Hey everyone, and welcome to this explainer. I am absolutely thrilled to break down some really fascinating AI news with you today. We're going to be focusing on a major breakthrough in automated biomedical screening. Specifically, we'll be looking at a brand new study that demonstrates exactly how using a coordinated team of AI models can dramatically improve accuracy when researchers are hunting for highly specific clinical data. It's a real game changer.
So, to set the stage, let's start with a massive number 36 million. That is the amount of citations currently sitting in the PubMed database right now. Just to put the sheer impossibility of that into perspective for a second, if a human researcher sat down and read one abstract every single minute, 24 hours a day, without ever sleeping, it would take them over 68 years to read them all. We are literally producing medical literature at a scale that is completely beyond human capacity to manually process.
Which brings us to Section 1, the literature review bottleneck.
This bottleneck gets infinitely worse when researchers are looking for very specific, complex criteria. Take something called the EQ-5D, for example. This is a standardized tool used for measuring a patient's health-related quality of life across 5 domains: mobility, self-care, usual activities, pain or discomfort, and anxiety or depression. The catch is, searching for this in abstracts requires a really high level of clinical interpretation. You can't just Control F or type EQ5D into a search bar, right? An abstract might casually mention the tool without actually reporting the results, or it might use a weird variant name like EQ5D-3L. It completely breaks your standard keyword searches.
Right now, systematic literature reviews are the gold standard for gathering the evidence we need to make massive medical and financial health decisions. But because of that mountain of data we just talked about, the old manual screening process is failing. It's become agonizingly slow, it consumes incredible amounts of resources, and frankly, it's highly exposed to human error. It perfectly illustrates the core conflict today: the old way of slow, inconsistent, manual human screening versus the urgent, critical need for scalable AI automation. Manual screening just creates this massive cognitive load for human reviewers, which leads to fatigue and inconsistency. We urgently need an automated system that can reliably handle that initial triage phase.
All right, Section 2, enter the LLM ensemble. This brings us to the real hero of our explainer today. We're looking at a new arXiv preprint study that tackles this exact screening bottleneck head-on by using a team of Google large language models. The core proposition of the paper is captured perfectly in how the researchers describe it. They propose a multi-phase framework that integrates few-shot prompting, weight ensembling aggregation, and a soft stacking meta-classifier. Okay, I know, that sounds like a mouthful of incredibly dense academic jargon, but don't worry. Stick with me because we're going to break down all of those terms over the next few minutes so you can see exactly how elegant this solution really is. First up, who's on the team? Well, the researchers evaluated 9 different models from Google's Gemini and Gemma families. They range from the massive, highly capable Gemini 2.5 Pro all the way down to the tiny, lightweight Gemma 3 1B. I actually want you to think of this list kind of like interviewing candidates for a medical board. When you're trying to diagnose a tricky, borderline case, you don't just want one doctor's opinion, right? You want a diverse panel of doctors to bounce ideas around and ensure you reach the absolute right conclusion.
Moving into Section 3. A 3-phase AI framework. Let's peel back the layers of how this AI panel is actually organized to work together. The pipeline operates in 3 sequential phases, and each one addresses a specific failure point you'd normally see with a single model AI. Phase 1 is few-shot prompting. This is where the researchers basically trained the models by showing them 40 carefully labeled examples, 20 positive and 20 negative, just to align their baseline understanding of what an EQ-5D study actually looks like. Then we have Phase 2, weight ensembling aggregation, and Phase 3, the soft stacking meta-classifier. Let's look a little closer at Phase 2.
So Phase 2 utilizes something called weight ensembling. As you can see, this is a technique where multiple AI model predictions are combined, but each vote is scaled by the model's historical accuracy and confidence. After testing all 9 of those models, the researchers isolated the top 3 performers: Gemini 2.5 Pro, Gemma 312B, and Gemma 327B. Instead of just doing a simple Democratic majority vote, this framework assigns dynamic weights to each model based on how well they performed during testing. Basically, the smartest, most historically accurate models get the loudest vote. That prevents one confused or underperforming model from dragging the whole group down.
Next up, Section 4, decoding the meta-classifier. So, what happens when the AI ensemble isn't entirely sure? To process that inherent uncertainty, the researchers used a clever technique called soft stacking. You see,
The base models don't just output a hard yes or no. They output mathematical classification probabilities. Soft stacking means training a separate meta-classifier to ingest these soft probabilities and confidence scores to make the final prediction. In simpler terms, think of soft stacking as a highly experienced hospital manager. This manager doesn't just look at the final diagnosis. They look at exactly how mathematically confident each AI doctor is before making the final official call. And the crucial takeaway is revealed when we look at what influenced this manager the most. Check out these coefficient weights. The soft probability from Gemini 2.5 Pro had a massive weight of 2.213. The probabilities from the Gemma models were also really strong drivers. But look down at the raw confidence scores. They provided almost no value, with weights of 0.253 or lower. Basically, the raw underlying mathematical probabilities from the models drove the final decisions far more than the model's own stated confidence.
Which takes us to Section 5, Performance, Runtime, and Costs.
Because, let's be real, you can design the most elegant AI architecture in the world, but it literally doesn't matter if the real-world performance is poor or if it costs too much to run. Here is the massive breakthrough. Gemini 2.5 Pro all by itself achieved a very respectable 0.71 F1 score, which is just a metric that balances finding all the right studies while successfully avoiding the wrong ones. But the weighted ensemble, it hits a 0.74 F1 score alongside a 0.74 accuracy rate. This proves definitively that a team of AIs, properly weighted, outperforms the very best single AI working alone. The ensemble got noticeably better at both finding the needles in the haystack and ignoring the hay.
But we have to ground this research in reality, because trade-offs are a very real thing. Running a batch of 200 abstracts through the heavy Gemini 2.5 Pro takes over an hour and costs about $5. Not terrible, but look at the lightweight Gemma 3.4B model. It processes the exact same batch in just 12 minutes for only 7 cents. This gives researchers a super practical balance. If you have the budget, the ensemble gives you maximum accuracy. But for resource-constrained settings, those lighter models still provide highly effective screening for literal pennies.
Finally, Section 6. Takeaways for AI developers. So, how do we translate all these academic findings into actionable advice if you're building AI screening pipelines today? Well, here is your blueprint. First, treat ensemble architecture as your new baseline. Do not rely on just one model anymore. Second, replicate those few-shot templates carefully to ground the AI in your specific clinical criteria. Third, implement strict confidence thresholds. Fourth, and I can't stress this enough, this is absolutely vital, route your low-probability abstracts to human reviewers. You shouldn't deploy this blindly. Human experts absolutely must stay in the loop for those tricky borderline cases. And finally, log all your model outputs so you can measure concept drift as medical terminology evolves.
To really solidify the immense value of this framework, I want to reiterate the paper's final conclusion. They stated, the findings suggest that an ensemble-based LLM setup is a reliable and scalable approach for automating screening in biomedical research. This entire three-phase approach, the few-shot prompting, the weight ensembling, and the soft stacking, is clearly paving the way for the future of how we handle medical literature reviews. And with all that in mind, I want to leave you with this thought-provoking question to chew on. Are we ready to trust a panel of AI doctors to write the first draft of medical history? It's an incredible step forward for efficiency, for sure, but the human element remains as vital as ever to verify those tricky borderline cases. Thank you so much for joining me for this explainer. I really hope it brought some clarity to this complex topic. And as always, keep exploring.